Hello, and welcome to the stream, or video if you're going to be watching this from YouTube, which I'll eventually upload. I want to start a small series on some game design concepts, because I feel like a lot of times I get questions about how do I manage objects and how do I move things around and such. So I figured I would make a series on that. Today I'm going to be talking about object storage, how we go about handling that. I have a basic Pixel Game Engine template here, and if I run it, it just displays a blank screen. There's nothing in the onUserUpdate or onUserCreate functions, so nothing to see there quite yet. However, one thing we have to do in games is handle a lot of objects. When storing objects in C++, we probably want to put them in a container called either a class or a struct. A struct can be specified by saying struct and then the name of the structure you want to name it by, and a class in the same way. The reason why I mention both is they function a little differently from each other. For the sake of simplicity today, I will be using the struct. But a class has the ability to define things. I would call it inheritance. Classes can have inheritance while structures cannot. That doesn't matter too much for this video, but in the future it might. So the first thing I want to talk about is how we store these structures. For now, we're just going to say every object in the game will have a sprite pointer, which will be the sprite itself. I'm actually going to call this a decal pointer because we're going to use decals today from the Pixel Game Engine. I'm also using the namespace OLC. This way I don't have to type OLC : in front of all the OLC specific stuff. Although, it's a good habit to not use namespace if you don't want to pollute the namespace. That way you're not, you don't run into conflicting names if you want to use a specific name. But, in my case, I think it's more convenient. I'm also going to be making a float vector, which is going to hold the position of an object. The first thing I'll do is just demonstrate how to create one of these objects. So we'll start with something basic, like a player. If I wanted to create a player, I would type the name of the struct or class, followed by the name of the variable itself. I'm actually going to put it in my Pixel Game Engine class. The reason why I want it here is so that it's in the scope of the Pixel Game Engine class itself, and not in just the onUserCreate function. We want this player to be available after it's created. The difference between putting it here and putting it here is that in here, it will not be destroyed when onUserCreate ends, which would be bad because, well, the player needs to exist the entire time in the game. I made some sprites. I made a bullet, I made a space alien, and a spaceship. I'll show those real quick. Here's our little space alien guy. I have a spaceship here, and I made a little bullet for the spaceship. If I just quickly overlay the spaceship, let me see if I can do that real quick. You'll notice that the bullet is lined up with where the shooting part of the ship comes out. I don't know what it's called, like a blaster or something. And that's a little intentional. That way it's easy to position for later. So with a player object specified, we're going to actually populate its variables now. It needs a sprite and a position. So in onUserCreate, when the game is created, we're first going to define the sprite itself. which is the spaceship here. In Pixel Game Engine, I can define a new sprite by saying new decal, new sprite, followed by the name of the sprite, which is space underscore ship.png. Now that we have our, I'm actually going to name this spaceship sprite. So for a player object, the easiest way to define this is to use these curly braces. When you do this for a struct, any values that follow will correspond to defining these variables. The first argument will be spaceship sprite, and the second argument will be a position for the sprite to be, or the player to be located at. I need to use these brackets to create a new floating point, or float vector 2D vector. Yes. Let's put it at 32, 32. That's a good starting point. And this is how we can define those things. Now, in a class, traditionally you would use a constructor. You can also define a constructor inside of a struct as well by doing something like this. So, another way of handling this is to write it like this. This way, you're initializing a sprite provided to the sprite variable and a position to the position variable. And then instead of doing this, instead you would do something more like this. Defined in a similar manner. It's one and the same. In the end, your preferred method of initializing will end up with the same result. Displaying the player on screen, since it's a decal, I'm going to be using the draw decal function. The draw decal function takes a position, so we'll use the player's position and the player's sprite for the decal. We'll just draw it at that location for now. You can make sure it runs, and that's displayed at 32, 32. We also need a default constructor if we're gonna use this method. Nice VS Code theme, thanks. So that's for one object, but in games you typically have to store many objects. So to do this we need a container. I'm going to go through 3 types of containers that are typically used in C++ for storing items. The first is probably the easiest to use. It's called a vector. The vector is a dynamically sized storage container which you can add and remove from and will dynamically allocate memory as needed. So it's got a lot of built-in functionality, but that also means there's a lot of side effects behind the scenes, which comes into play when you start doing more complicated behaviors. To initialize a vector, it comes from the standard library. You have to specify in less than greater than size signs the type of the elements you want to store, and then you have to provide a name for this list. So I'm just going to call this the object list for now. So With an object list, our goal is to now store more than just one object and be able to iterate through all of those objects and display them on screen. A common thing I like to do in my games is not just have one object list, but a couple of object lists that are separated by type. So you may have one list for enemies, you might have one list for bullets, and you might have just the player by itself. It doesn't need a list because there's only one player. So that's typically how I would divide games up. But another way to divide games up is to use polymorphism, which is beyond what I'm going to discuss today. So I think for today, we're just going to do something like this, where we have two lists. Because we can have multiple enemies on screen, and we can have multiple bullets on screen. And because of that, we need a place to store a list of all those objects. With these two created, we can now create some enemies. I'm going to use a for loop to create 8 of them. If you want to avoid allocation calls, then you can pre-initialize how many, what its starting size is using the reserve function. The reserve function, if you say, let's, like, 32, that means this vector will allocate at least 32. Yeah. It might allocate more than 32, but it's guaranteed to have at least 32 spots before it has to reallocate itself dynamically and all the memory shifts around and copies happen. Yeah, if I know I'm gonna need a certain amount of space, and I'm probably not gonna need more than that, I might just allocate it in advance. That way it's more of a static structure. To add to a list, we can use either push front or push back. Or excuse me, that's for lists actually. We'll get to that. For vectors, we can only push to the back. Pushback means they'll be inserted at the end of the vector. And we're just going to make 8 of these guys. I have a sprite for enemies. It's called space_alien.png. So I'm going to go ahead and create an enemy sprite called space_alien.png. And then I can use that to initialize our object here. By default, pushback will require you to specify an object, so I'm going to go ahead and do that here. And for the locations, I'm actually going to randomize it. I'm going to make it... We have a game that is 256 pixels in width, so I'll do from 0 to 256 minus 32, so it's not like going off the edge of the screen. I'll put them at a height of 16 for now. And... oh, it doesn't like this. Because I'm using a float, but it wants ints. Or I'm using ints and it wants floats, so I have to manually cast that. So yeah. Or I can use the constructor again. It's if I were using classes, I could do it like this too. It's essentially the same thing. For drawing, I can do something very similar, except I'm not gonna assume that this amount of enemies in the list is 8. I'm gonna say the amount of enemies in this enemy list is stored inside of the size method, which means however many are in here, we're gonna draw all of them. I'm gonna use the draw decal function again, and to access any of the elements in our list, we have to use the hard brackets and specify the letter I, because that's going to be our counter that goes up. Then if we type a dot, we now have access to that object at that specific element. So at element I, we have access to its position, and then its sprite as well. Like so. Yes. There is an iterator version of the loop, the for loop, which I will demonstrate in a second. You can see all of our little aliens are created just at a couple of random positions. 1, 2, 3, 4, 5, 6, 7. I only see 7. That's a little oh, I think that's 8. You can kind of tell they're overlapping. It's a fatter looking alien. The iterator version of the for loop for a list in C++, you specify what object you're going to get out of it. And you have to include this ampersand. This means it grabs a reference and doesn't make a copy. Without it, which I'll explain in a moment. So the name of the variable, and it's a reference to an object, colon, and then the list. From here, of course, we're not accessing elements from the array by position anymore. Instead, we're getting the object directly. So now I use draw decal object dot position, object containing whatever object we're currently looking at in the iterator. It's common for folks to forget this ampersand, and when you do this, it actually makes a copy of this object, which means if I were to try to do something weird, like modify this object's position inside of the loop here, let's just make it some value where we know it's going to be at a weird spot. Like, let's try to put every object at position 166. Because this is a copy, oh wait, I should probably do that afterward. Even though we're telling it to modify it, it's modifying the copy's position, so on the next frame, we're actually seeing where it was originally. So, however, using a reference, if I were to modify it, after the first frame, all of their positions are going to be at 166, so now we're modifying a reference to the objects instead. It's very important to distinguish that. C++ is a little tricky in that regard, in that copies and references can be really confusing if you're not careful. Copy is very much less performant, yes, because after this for loop is done, every single one of those objects get destroyed right after in memory, so you do that a couple thousand times and you're quickly going to see performance drops in unexpected places. So there's a lot of gotchas when it comes to that. So we can do something similar for bullets. However, bullets are created dynamically. They're created based on player input, whenever the player happens to want to shoot. I'm going to start by using the getKey functionality of the Pixel game engine, and we're going to look at key space for this, a pretty common one, I think. We won't do held for now. We'll just do whenever we press it. Let's make a new bullet. I'm also going to move the player down because I don't think the player should be at the top of the screen where the enemies are. Let's see, our height is currently 240. Let's do 180. That's a good place. So just like for enemy lists, I'm going to do a bullet list dot pushback, add a bullet to the list, create a new object. This time we're going to use a bullet sprite, which I have, called bullet.png. Dang it, can't type. Should have copy pasted. Any static code analysis? There is one thing, and it's compiler dependent. If I can remember real quick. I want to say, if we were to do G++, there are warnings, right? There are all sorts of warnings. I think the one we would want, yeah, I'd have to go look it up. There are ways to get to say, hey, this is probably not what you want to do. But I think it's very compiler dependent. And I had it at one point. I think it ended up being more annoying because I'm like, I know what I'm doing, so I removed it. Yeah. I don't like using it because it gets very annoying. Alright, so I have a bullet sprite that I can use here. And our object needs a position. So the position is actually going to be based on the player's position. So I will put player.pose here. Also, it doesn't like bullet sprite because I created bullet sprite here in onUser create, but it doesn't exist when I get here. So I'm actually going to create these decal pointers in the instance of the Pixel Game Engine instead, and then just reference them that way. That way, they're available to the whole instance, in which case our bullets need to reference that bullet sprite. So we can make a bullet. It's not going to move or anything yet, but we'll get to that. Oh, we also don't display our bullets. That's a problem. Let's draw those too. Similar idea here, except we're iterating through a bullet list. I'm going to get rid of the changing positions. So we're iterating through enemy list, draw all those, iterating through bullet list, draw all of those. If I press space, we actually create a bullet at the spaceship position. Let's do some more user input to make this a little more interesting. I've been meaning to try this. I think this would be kind of cool. We'll add to the player position X based on get key. We'll use the left to right arrow keys for now. We're seeing if they're held. And we're going to do right being +1 and left being -1. So be held returns a boolean, and booleans, when converted to integers, are 1s or 0s. So if we're holding right, this would be set to 1, and if we're not holding left, this would be 0, so 1 minus 0 would be 1. And if we're holding left, this would be 1, so if you did 0 minus 1, you'd get -1. So this is like a little shortcut to having an if statement of, if I'm pressing right, go right. If I'm pressing left, go left. And we're zooming because we're going really, really fast. I'm going to take this value and multiply it by felapsed time, which is going to lock it down to how much time has passed in seconds, which means now we can multiply this by some kind of ship speed that we actually want. Let's move at like 50 pixels per second. Yes, it's very important when doing movement with game engines. You actually lock it to the the speed of the engine reports, and not just an arbitrary amount based on how much FPS you're getting. If I press space now, we can create multiple bullets in different places. So now let's make a move. We already know how to iterate through objects, so in bullet list here, before I draw them, let's update their positions by incrementing Y. Or decrementing in this case, so they're moving upwards. Let's just use a value of 8 for now. Again, we'll have to multiply that by felapsed time. Actually, bullets are pretty fast. Let's move faster than that. Let's move at 160 pixels per second. That sounds like a good amount. So yeah, we now have some bullets and we can now move around. We can't shoot the enemies yet, but we can make some very rudimentary collision detection here. We have to keep in mind that the bullets will go off screen and won't disappear yet, so we'd have to make logic for that. I'm not going to bother with doing object inheritance for now, but traditionally what you would do is you'd make, if you want to go the object-oriented route, you would make it so bullets would be their own subclass of objects. That way they can have their own behavior, and that way you can define what happens when they have their own update function, when they're moving off screen, things like that. But today we're just going to confine all bullets will behave inside of this loop, and all enemies will behave inside of their loop. And you could actually program in this way. It's not bad, it's just a little more messy. The idea of object inheritance is to make it so the code, the main code, looks cleaner. You decouple the data, where all the objects are stored versus what their behaviors are. So this is not a great programming practice, but it does simplify a lot of things because you can kind of see right away that you're modifying bullets here. So this is a simplification for today. We're going to say if the position is less than, I'm going to wait till they're a little more off screen because the sprite actually is 32 pixels tall. So when their Y position is at 0, the bullet, like the top of this bullet, is actually still on screen. Like this is what it would look like at position 0. And then at position -1, you would see, what's happening? I'm on the wrong layer. You would see this, or, hello? You would see this, and then on the next frame you would see this, and so on and so forth. So realistically, we'd have to wait a couple extra pixels beyond 0 before the bullet is off screen, otherwise it would disappear kind of prematurely. So I just put -32, as that's the actual sprite height. So now we have to destroy it. And here's the tricky thing about lists, is that destroying could mess things up. So a common way to fix this is to either store everything that will be destroyed and do it after you're done iterating, or cleverly iterate such that you are still within the bounds of the list after destroying things. Because when you destroy something from the list, the size of it shrinks down by 1. So that's what you have to remember. So unfortunately, we can't use an iterator for this kind of paradigm if you're going to destroy something, because then the iterator will be way off and it will no longer be valid. So I'm actually going to go back to counting using indices so we can see what's happening. So I'm going to use the bullet list size here. And what we could do is grab a reference to the bullet, like so. So we kind of get a similar like setup that we did with the iterator here, where the object variable is storing the element from the bullet list. So to destroy something from this list, this vector, we use erase. Erase requires an iterator. So funny enough, we're using an iterator in here to tell it which position to destroy. .begin contains where the first element is, and then if we were to add what our current element index is, that would be the position that we have to erase in memory. Once we do that though, we will actually have one less item in the list. So what's going to happen is everything shifts over, and so we need to account for that by subtracting by 1. I can do this very quickly as a shortcut by typing minus minus here, or I can just do it right after. Minus equals 1, minus minus, they all mean the same thing. Doing it here would also work as well. It's kind of an all-in-one. Quick little visual. If I can get the right screen, that's not the right screen. That's also not the right screen. Where am I? Oh, here we go. Yes, this is my drawing tablet. This small rectangle represents various positions of our list we made, and each one of these has, let's say, a bullet in it. So when we want to destroy a bullet, let's say this bullet right here makes it off screen. Now logically we could say that the bullets that we create, they will be destroyed in this order. And so that's an optimization or assumption you can make, and as long as that's the case always, then you could do some optimizations there. But let's say it hits an enemy, then technically this bullet might get destroyed before the bullet back here was created. When you destroy this element, it's no longer valid, and erase will actually copy all elements back over. So erase is actually a little slow in that sense, in that everything will move down by 1. But if this happens, then you're going to see this last element here will become the deleted element. So your actual size of your list is now 1 less. So what that means is we have to subtract 1 because the size is now 1 less before we continue iterating. And by subtracting 1, our pointer, let's say our I was here, right? This was what? I equals 3. 0, 1, 2, 3. So normally the for loop would make I set to 4 here, but then we force it back to be 3 again. And because all the elements shifted down by 1, we won't accidentally skip a bullet for 1 frame. This is a pretty important concept and happens a lot with like dynamically managed lists. Yeah, and I would agree. Sometimes these like all-in-one snippets can be a little confusing to figure out what the heck's going on. So by doing this, we make sure we're always reading through every element. We can delete stuff from the list without causing memory errors. Just for a sanity check, let's also draw the number of bullets on screen, just to make sure this is working properly. I'll use drawString decal here, and draw it at position 0, 0. We'll just simply draw the number. I'm going to convert it to a string as well. That way it can actually be drawn. So we'll just have the number of bullets in our list. So 1, 2, 1, 0. So you can see I can shoot, and as the bullets go off screen, the number decrements, which is what we would expect here. None of the bullets are doing anything weird. Like, if there was some kind of memory corruption, then we might see like bullets jump around in position, or maybe one might flicker. These common problems happen when you like skip an element in these lists. So that's something to keep in mind. And this is basically how we handle multiple objects. This is where I was going to end this series, but then I thought maybe I should talk about some of the other types. Now that we've implemented this in vectors, there's 2 other structures I would like to cover in regards to making this work, because there are other ways to do this. One way to do this instead of vectors is to use what are called standard lists. Lists come with one benefit of not having to dynamically reallocate itself. Instead, every object has a pointer to every object going forward. So this means when you insert something in a list, all you have to do is change the pointers of the previous and next elements. And you can do the same. You can add from the beginning or the end. The problem with lists, though, is you have to iterate. You can't like choose one specific element in the list to you can't use indices. Like you can't pick the fourth element from the enemy list. You have to start from the beginning and go to the fourth element by iterating to it. That's the only downside to it. So you'll actually see down here, my code now has some errors when I'm using lists because we can't use indices anymore. So, in this case, we would instead have to use an iterator to count through these again. But then that presents another problem because I did say that we're not going to be able to properly erase things from the list if we have to go through an iterator, which is kind of unfortunate. But then the way around this would be to track what we have to delete and then delete it afterwards. So the way I would do this is have some kind of well, actually, I think there was something about this where oh, I know. Instead of iterating like this, we can use the standard list iterator itself. That's what I wanted to talk about. So every standard list object you create, the template comes with an iterator for that list too. So this is going to be a for loop where we set up the iterator from the beginning of bullet list, and we're going until the end of the bullet list. So while the iterator is not at the end, we're gonna increment the list. Now, doing this is kind of like using an index, but instead, the iterator is going to be pointing to some object pointer. So really, instead of a C++ object, now we have a pointer to said object in memory. Why are you complaining? Oh. We could just use auto here, I think. What this actually created was a standard list object iterator reference, which means that we can just make it realistically what we would do is we would type IT here, but I just wanted to use object itself, so I just made it equal to IT itself. But since it's a pointer now, we can't use dot anymore. We have to access it using these arrows, which means it is indeed a pointer. It's no longer an object. Do you have to increment before using it? No, you shouldn't have to. The begin is like your index 0 of the list. It should be pointing to the first element right away. So instead of erasing from the beginning to an element, now we just type it, and then we have to still do the same thing. We have to subtract 1 from the iterator, because now it's going to be 1 less than it was before, or I can do it minus minus here. So lists are a little weird in that regard. There's an iterator for vectors too, and it would work in the same way. Oh, we got a seg fault. Let me think. Well, this iterator is probably invalid the moment we erase something from it. Yes, but in a for loop, this statement executes after the code has been ran. So, in a for loop, this always runs at the beginning. Then this gets checked. This is the condition. Then this code is ran. Then this occurs. And then the condition repeats until the condition no longer applies. Yeah, that's the order of operations. This, however, does not work. Let me think for a second. Why that would be. Let's go to the internets for this one. Oh, erase will return the iterator. I forgot about that. So, yes, erase returns a new iterator containing what the element should now, or what the iterated list should be now. That's what it was. Okay. I just used CPP reference there. Very handy, but it's kind of technical, which is why I don't recommend using it for a beginner, because you have to actually already understand all the nuances behind it. Cool. So that's what I was missing. The last thing I wanted to show was not only can you use lists, so lists are more performant when you have to add stuff to it constantly. And another cool thing you can do is, if we wanted to, with a list, we can also push it to the beginning instead of the end of the list. Because of how lists work, they just are pointers to each other. You can put it at the front if you want to. I don't know. It's literally the same thing in our scenario. Doesn't matter here. The last one I want to talk about is something a little more archaic. It's standard array, which is literally just your basic array. Arrays are fixed size lists and have no dynamic allocation to them. So that means in advance we have to know how many we want, and it cannot exceed that amount. There's some obvious limitations here, like once we reach the max, we obviously can't have any more than the max. If I specify 8 here, if I specify 8 here and try to shoot 9 bullets, we have to include some programming for what happens. However, fixed size lists are good in the sense that you will never have a program with expanded memory beyond what you're given here. So it keeps your memory footprint small, but now you have to make sure when you try to add a ninth element, what do you want to do here? And I'll demonstrate the same game by using fixed size lists as well, because sometimes you might want to do this. Again, it's a little more crude, but it's one way to do it. So firstly, there's no pushback. Every element is already initialized. 0 through 7, those indices are available for you to put stuff in. So instead of pushing back to a dynamic list, now we say for each element, we're just going to set it equal to a new object we created here. In here, we can't push to a dynamic list of bullets anymore, so we'll do two things. Like I said, what happens when we fill all the slots? Also, how do we know which slots are still active or not? Well, we kind of already hinted at how bullets are destroyed. So what we can actually do is iterate through our bullet list and find a bullet that may be at a position less than -32. Oh, I also did make it so we can shoot the aliens. We can do that for this because I think it'll be kind of interesting to show how we can quote-unquote destroy elements but have it in a fixed size list. You can use some clever tricks for that. So we have to add to our list, but we don't know where in our list there is space for. I could type the number 8 here, but one cool thing about the standard lists is they actually do come with the size element. In C, you don't have that luxury. If just for reference, a C array looks like this. And when you type this, this is just a C array that has no sense of it doesn't know what its size is. You just have to know yourself. You have to program that size in. But standard array adds a few convenience functions, but still a fixed size. So we're going to see if any of these bullets positions .y is less than -32. If so, we're actually going to insert a new bullet at that position. Our position is going to be the player's position for the bullet. Like that. When we do this, two things will happen. The object that this originally was pointing to will be deleted because C++ objects will automatically delete when their variables no longer reference something, and a new object will be made at a new position. Another way we could do this is to actually just modify the position directly, which is a little faster actually if we want to optimize things. But that's essentially what's happening here. A design to avoid iterating the bullet list twice. In the sense of deleting things from the list. Is that what you're asking about? Another convenience of the standard array is we still get the iterator functionality, which is cool. To avoid iterating the list twice while still deleting stuff, you would have to do the decrement index method if you want to avoid it twice. Does that answer your question? So, let me see here. I could change this to be an array iterator if I wanted to. I think. You have to specify the size here, funny enough. But there is no erase functionality for arrays, so it's kind of pointless to do anyways. So I'm just going to simplify this back down to iterating as if it was an index-based list. Because what I'm going to do here is still make this a bullet reference. I'll point to the index within the bullet list that matches. And these are no longer pointers, so I'll put those back to being dots. And we're no longer going to check and actually erase things from this array. Partly because, well, it's a fixed size anyway. If it keeps going on into oblivion, we really don't care at that point. So what we should actually see is that the bullet list size will always be 8 no matter what. Which also means we need to probably initialize our bullets to not be at a bad position. These objects that are created can literally have values that are anything. It could just be like corrupted memory. So what I'm going to do at the beginning is say for every element in the bullet list, let's just make up some values. And I'm just going to place those bullets at some position off screen, like really, really far away. That way, when we create a new bullet, its Y position is already really far away. And like I said, it's kind of a trick you can use. Sets a boolean if that boolean is set during the deletion iteration. Instead, erasing the element, it replaces it and unsets. Oh, I see what you mean. If you wanted to insert a bullet without having to iterate here, and then having to iterate here for actually drawing everything. I see what you mean. Yeah, you can like mark a position, or you can mark that you want to put a bullet somewhere. That is true. That does require a bool. Add bullet is what I'm going to call it. So yeah, if we want to, we can just request a bullet. Add bullet gets set to true when we press space. And then down here, if the position, let's do it at the top of this logic actually. If for some reason the position is less than -32, and add bullet. Let's add our bullet and set add bullet to false. Again, working with fixed size lists or fixed size arrays means you have a little more like, it's kind of old school programming. But yeah, that is a pretty clever way to do it as well if you just want to iterate one time strictly. Because the way I see it, if you iterate through this list 2 times, you're going to end up with an O2N factor, which isn't a big deal to me. Yeah, it does save some time. In the grand scheme of things, it's not too bad. Let's just set the position directly to the player position. Like that. And that would effectively be the same thing. So our list is 8 in size, and I'm trying to shoot more than 8 bullets, but what's actually happening is until a bullet, and this is kind of hard to tell, so maybe I'll reduce the size down to like 3 bullets. When we try to shoot the 3rd bullet, add bullet gets set to true, but it won't, or the 4th bullet, it won't happen until the 3rd bullet goes off screen. So I'm going to press space a lot here. So that 4th bullet actually came out when I stopped pressing space, which is kind of funny. So, because it waited until all 3 bullets were gone before trying to create a new one. But yeah, that's essentially one way to make it work. If I wanted to fix that, I would just have to add a little exception. If we release the key, obviously the bullet should not be shot. And I can actually change this now. Funny enough, we kind of auto made this to work almost. Except this could happen every frame, so we'd add a timer. Call it the shot cooldown. Every time we shoot a bullet, we'll just set the shot cooldown. That way I can just hold down the space bar instead of pressing the space bar a bunch. We'll set to like 0.5. And then the condition would become if shot cooldown is less than or equal to 0. And then every frame we can reduce the shot's cooldown by the amount of time that has passed in seconds, which is stored in this felapse time value. So if I hold down space now, it shoots a bullet every half a second. And it's actually impossible for me to shoot 4 at that speed. But if I stop holding space, it no longer tries to make a bullet after I've already held down space. Let me make this a little faster. You could unset add bullet at the end of update too. Oh, you're right. Yeah. That's why I love programming. Plenty of ways to do things. Yeah, we just check every frame, and then if we don't, on the next frame, we just assume that you're not holding it again. You're either holding it or you're not. So, yeah, it's just a switch you're either holding down or you're not. So if I let go now, it's not creating that 4th bullet randomly. Cool. If I just want to add some rudimentary collision, then, well, firstly, what I would do is I probably don't want to use this iterator anymore, because once again, I would be deleting, well, actually, we can iterate because we just delete it to someplace off screen. What is killing an enemy other than sending it to a place in oblivion? For this though, we'd have to iterate through every bullet for every enemy. And this is where you can do things with optimizations, of course. But the naive approach to doing this is to iterate through every bullet while you're inside of every enemy and see if that bullet is now colliding. Of course, the impact of this won't be too bad unless you have a bajillion bullets on your screen or a bajillion enemies. So, and there are ways to optimize this. You'd have to do some clever planning with, like, you can use the X positions of your bullets, and you can bundle up your enemies based on their X positions. And then based on that, you can only check certain enemies within those pools that you divide the enemies into. Yeah, it would just be contained, wouldn't it? If you want to go a step further, you would just add bullet in here. It would never have to leave the scope of this function, because it'd just be turned on for that frame, and then if the logic works out, the bullet gets added, and then it's a reset. If bullet lit, what am I doing? So we'll call this the bullet. Inside of iterating through every enemy, we're going to see if any bullet happens to be within this, like, box we made of the enemy sprite itself. So I'm just going to do some very crude boundary checking here. If the bullet, I like to do it this way. I like to check the bullet's position relative to the enemy. If the bullet's position is greater than or equal to the enemy's position X, and the bullet position, ooh, I didn't think about this. It's in the middle, isn't it? So let's add, there is a sprite width and height value, but I think it makes code look really messy when I add a bunch of those in. So I'm just going to use a hard-coded number here of 8. The sprite is 16 by 16. So if I do something like... And the width of the bullet is only 1, so realistically, we're just checking the bullet's raw position based on its halfway point. So I'm just going to use +8 here, because that's really where the bullet is centered on. And check if it's greater than or equal to the enemy's position and less than or equal to the enemy's position plus 32, or 16, excuse me. This enemy sprite is 16 by 16. And I'll allow some generosity. There's an extra pixel on both ends that's actually not visible, but we'll give the player some freedom there. The bullet's position Y, the Y position also has to be good. So the Y, I made the bullet so the top is actually at the top, so we can just use the straight up the Y as the hit position. .y plus 16 again. And again, I do want to hard code this because... Oh, not the bullet's Y. The enemy's Y. Then this is a hit, so I'm just going to move the object to oblivion, essentially. Someplace where it's impossible for it to get hit anymore. And that would be consider it deleted. We could also add like a score value if we really wanted to. And you're right, we wouldn't need this anymore. If we're just gonna set it to false every frame. And that should allow for some rudimentary bullet collision. Actually, we didn't make the bullet disappear, so it just charges through the enemy. That's a twofer. There we go. I also want to talk real quick about pointers versus objects, because I get this sometimes too. Some people want to use classic C, where instead of storing these like objects that are created using C++, they want to just use these pointers to store things instead. There's one downside to using pointers, in that you are literally required to manage all the memory yourself. This new keyword is literally the malloc of C++. It allocates memory that will fit whatever structure you declare it to be. So, if I want to use pointers to store everything, I would have to type the new keyword and then specify all the parameters for that. And the difference between this and what I originally did was it's not handled by C++ anymore. If I make this bullet list, like the first bullet, point to a new object now, like how I did... Where did I do that? I know I did that. Oh, maybe I didn't. Okay. But if I were to make it point to a new object, now the previous object is now just hanging out in memory somewhere. And this is called a memory leak. It's a feature. You're not wrong. So this is just something to be aware of. I'm not against using pointers, but I definitely have a better handle on using C++ objects now, and actually prefer them because it keeps things clean. But our game could technically operate in the same way. There's nothing wrong with storing a list of pointers. One cool thing about storing a list of pointers, actually, is if you were... I guess we can talk about this, because this is actually a big gotcha of using a vector as well. Because remember, vectors reallocate dynamically in memory. If you try to add objects to your list in a loop, and the list or the vector happens to reallocate itself, then all of a sudden every object in that list may no longer be valid memory. So this is the one catch where using pointers is nice, because every pointer has already allocated memory in some place in space. and all the vector would be storing is the memory address. So memory addresses are always valid, even though the data holding the memory addresses moves to a different spot. Like, you're still pointing to valid data. It's something that I've run into in the past and is a little bit tricky with vectors. The easiest way for me to demonstrate that actually is by doing a separate project real quick to show what I mean. Anyways, this is done. I'm happy with this. And if you use pointers, it's not like anything bad happens. You just have to remember to remove the memory if you ever don't need it anymore. Like, let's say we were actually deleting objects, then we would have to use the delete keyword followed by whatever we're trying to delete, like the first bullet or something. That would free the memory. If you ever wanted to add an object, delete an object. It's a little more annoying and complicated, though, than letting C++ do it for you. Hey, nice to meet you too. Thanks for hanging out. Have a good one. I think I got through everything I want to cover tonight too. So, simple example, we shoot aliens, we handle objects, multiple objects that is, and organizing code in this way is pretty handy. I'm going to try to do something about how to move a lot of the behavior like code into an actual class using behavior based parameters. Sometime, whenever I feel like it. Anyways, that's that.